Hello and welcome to Coffee and Control, the podcast where I find fascinating people from within the world of control and convince them to answer all of my questions. I'm your host Lucy Hodgins, and in this bonus episode I got to talk to a bunch of super interesting early careers researchers at the Meet the Faculty Candidates poster session at the Conference of Decision and Control. So this is the chance for graduate and postdoctoral researchers that are looking for an academic position to showcase their work and interact with potential future employers. But it also allowed me to meet lots of wonderful people and ask them lots of questions. This episode is going to give an overview of the research that they are doing, and I have put links to the papers in the description if you would like to get in contact with them. So get ready to hear all about research in a wide variety of different areas, including strategic communications, traffic control, surgical robotics, reinforcement learning, estimation in networks, and a whole lot more with my guest today from the Meet the Faculty Candidates poster session.
Hi, my name's Amy Strong. I'm a PhD student at Duke, or PhD candidate actually. I work with Leela Bridgman. She's my advisor. And I'll talk a little bit about data-driven invariance using geometric methods. So essentially for invariance, we want to find a region of the state space that maps back into itself. And there are some great model-based geometric methods that are able to do that, but they have some failings in the sense that they can't always work with nonlinear systems or non-convex constraint sets. So we wanted to develop a data-driven method of finding an invariant set with deterministic safety guarantees. And the way we do that is by using the Lipschitz continuity of the plant to over-approximate the successor set of a region around a sampled point. So we essentially try to over-approximate where the system is going to map a region to. And then we try to prune down the entire state constraint set to an invariant set by finding where this over-approximation will map back into itself.
So the way that Amy does this in her work is to use a tree data structure, which is a set of connected nodes where each node has a single parent and potentially many children or leaf nodes. Now, each tree data structure corresponds to a particular pair of data points corresponding to the state at the current and next time step. And each level of the tree corresponds to a particular iteration of the algorithm. As Amy described, you start off with an over-approximation of the invariant set, and then at each step of the algorithm, you look at whether the norm ball of a given radius around the state at the next time step is inside or outside of your estimate of the invariant set. If it's completely inside, then the node remains unchanged. If it's completely outside, the point is removed from the invariant set. If this ball intersects partly with the invariant set, then the parent node gets divided into 2 to the power of n leaf nodes, where n is the dimension of the state space, and on the next iteration you consider balls with half the radius. Intuitively, this makes a lot of sense, so you're dividing up the state space and getting rid of bits that aren't in the invariant set, but this paper formalizes this mathematically and links it to the synthesis of Lyapunov functions. So in particular, her work provides a way to certify the stability of these kind of systems. And she does this by taking this invariant set and assigning a Lyapunov function value to each partition of this set. And this then gives a discontinuous piecewise constant Lyapunov function that can be used to prove stability.
So my research is on game theory and communication. So I consider, right now when we are talking, I am like a sender and you're a receiver, and I'm trying to tell you something about my research, and that's the message. And there may be a lot of background noise, but we work as a team because we want this message to be transmitted from A to B, point A to B. But in a game theoretic setting, maybe I have a different objective. Maybe I want to make your opinion biased in a certain way. Then how do I communicate? That's basically the crux of my research. So one example is let's say you have 2 driverless cars and you have a Tesla and a Honda. Honda is up ahead, so Honda can see the traffic up ahead, which is information that Tesla does not have and wants to have. So Tesla now asks Honda, how's the traffic? And Honda actually does not have an incentive to say the truth because it wants less cars on the road. So it would prefer that Tesla get out. So it is now trying to basically push Tesla to go, but it cannot outright lie, because then Tesla can be like, I'm not listening to you, I'm going to look at the prior distribution of how traffic is usually. So Honda does something that is just enough that it is better than what Tesla would do with just prior distribution, but it's still not honest.
So this is an example of something known as strategic communication, in which communication between two entities can be viewed as a non-cooperative game. So Anju examined this in the presence of noise and where the data to be transmitted is quantized, and was able to characterize the strategies of the two communicating entities at the Nash equilibrium. And it turns out there are quite a few interesting applications or examples of strategic communication.
But in this setting, it's more like, what if the senders are human, and so they are not fully rational, they are boundedly rational? How do you model that? And there's a model in economics which basically considers different levels of cognition. And so at each level, let's say I'm at level 2, I think that I'm the only one at level 2. Everyone else is below me and probabilistically distributed below me. And this kind of assumption, it ends up simplifying the problem a little bit. So we are able to compute closed form expressions, which we can't really compute for the original problem. But yeah, this is my highlight of the research.
I also wanted to mention that Anju's most recent paper modifies this setup slightly to consider privacy objectives, where the encoder is transmitting a message to balance fidelity with privacy in the presence of an eavesdropper, whilst the decoder just wants to minimize its own estimation error and doesn't care about privacy.
Yes, I'm Brian Block, and this is my research on constrained optimal control of distributed parameter systems. So what I'm interested in is looking at traffic as a fluid. So you can model traffic as a PDE, and then I design optimal control techniques to minimize traffic and to reduce traffic density. And so there's a couple different ways you can do that. One is through using variable speed limits, and another is through using control in automated vehicles to change how traffic adapts, how traffic moves. And so one big benefit of this is by defining the controller on the PDE, it's very computationally effective. And so we can get controllers and models that are around 200 times faster than real time.
So the crux of Brian's research involves defining controllers directly on a partial differential equation, or PDE. So in previous work, he used linear quadratic controllers to approach this problem by linearizing the system model. But the work he was presenting at CDC was able to deal with the PDE model more directly. So one standard approach to tackling this has been to discretize the model into a system of ODEs, or ordinary differential equations, and then apply control barrier functions and or control Lyapunov functions to ensure that the system stays within the safety constraints. In contrast, Brian's work presents a unified framework that combines control Lyapunov and control barrier functions in a way that enforces constraint satisfaction directly at the PDE level, which, as he explained, is a lot less computationally intensive.
So hi, I'm Declan Jacht. I'm working on extending LMI and SOS methods for ODEs to partial differential equations.
So LMI stands for linear matrix inequality and SOS stands for sum of squares. And these are both particular formulations that if you can transform your problem into one of these forms, then there are a bunch of standard tools that you can use to solve them.
So imagine instead of analyzing stability of a finite dimensional setting by testing negativity of a matrix, we're going to be testing negativity of an operator to verify stability of a PDE. And for this, we use the pi representation. We have our pi tool software, which allows you to convert the PDE to a pi, and then test stability using one of our many executives, as well as perform controller design and observer design. The next thing, extending this to nonlinear PDEs using sum of squares.
So pi stands for partial integral equation, and this gives a way of expressing PDEs in terms of the evolution of a higher spatial derivative of the state. The PyTools software that Declan mentioned is a free MATLAB toolbox that his group has developed that you can use to manipulate these kind of equations, solve pi inequalities, and design various different controllers. Declan's research focuses mostly on the theoretical side, so looking at how to apply these tools to analysing stability of various problem formulations, including multivariate PDEs, coupled PDEs, and those with delays or periodic boundary conditions. Also, traditionally, this pi formulation only holds for linear PDEs, but Declan's work has extended this idea to scalar quadratic PDEs, which can be used to model kind of fluid dynamics, population growth, that kind of thing. And in this case, you end up with a partial integral operator instead.
Hi, I'm Hamza. I'm with the University of Illinois as a postdoc currently. So my work is kind of summarized by two words, viability and adversity. So adversity really refers to anything that can mess your system up or make your life really hard. And viability is just us trying to survive in an environment like that. And a lot of my work applies to safe autonomy in robotics, especially with applications to surgery. So there's two big pieces, the theory part and the application-driven part. The theory really focuses on reachability, viability, and fault tolerance. So these are all methods that allow us to look at what might go wrong with the system, even if we don't exactly know what went wrong to even cause us to think about these problems.
So Hamza has published quite a few interesting theoretical papers, but there are two in particular that I wanted to highlight. So the first one examines the problem of real-time identification in the presence of degraded control authority. So this can be applied to nonlinear affine systems subject to phenomena such as actuator wear and tear, friction, input saturation, dead zone, that kind of thing. And the paper proposes an algorithm to identify these and counteract them as much as possible. Another paper examined the problem of identifying simultaneous sensor and actuator faults in cases where there isn't necessarily sensor redundancy. So the general idea is to fit a sensor degradation map between the expected and sensed output and then use this to test for sensor degradation. After this, actuator degradation is tested for based on the difference between the guaranteed reachable output set and the confidently reached output set. Then finally, the full state is reconstructed using a zonotopic Gaussian-Kalman filter, which is just a particular kind of estimator that makes use of the fact that the disturbances are bounded within a particular set.
In the second piece, we leverage a lot of these theoretical advances to be able to solve a lot of problems. I cherry-picked a couple from my work in robotic surgery. So part of this is looking at the thermomechanics of electrosurgery. This is a procedure that's used pretty much anytime you go under the knife. It's very ubiquitous, but you can't really mess around and try to learn how this works while operating on a patient. So part of the problem is how can we operate safely and also learn what the patient's specific tissue is doing.
This work relates to a paper titled Heat Conduction in Live Tissue During Radiofrequency Electrosurgery and examined how to model this phenomenon and estimate the various parameters.
And then there's another part on robotics right here where we have a very expensive, admittedly, system that has two pieces, so a general-purpose robotic arm and a very precise hexapod, as they call it. And this allows us to position an imaging system to do microscopy while being, under operation, basically. So trying to bring a lab and put it at the patient's bedside while they're being operated on. And the challenge here is that the tissue is curved, it's flexible, and it moves because the patient's breathing, hopefully. And that's kind of what we're looking at here. We can compensate for the motion and at the same time figure out exactly what their breathing rate is and their cardiac rate.
The basic idea here is to apply controlled probing forces to a region of the body and measure the resulting deformation. Hamza then uses these measurements to estimate something called electrostatic signed distance function, which gives a way of representing the 3D curve geometry of the object.
Okay, so I am Kirill Seshkar, a finishing PhD student at the University of Oxford, and what I'm really interested in is decision-making in biological systems. Basically, cells, whether they are bacterial or human, they take decisions which state to take. Are we being fast-growing, or are we trying to prioritize resistance to stress? The question is, what drives the decisions and what pushes the system from one state from another? The problem is biology is really sample inefficient, so you cannot just rely on making a lot of observations. But if we use control engineering and force the system through the states which are really interesting to us, then we will be able to understand the principles behind decision making and hopefully figure out the goals of the system and how to manipulate them to our own advantage, whether it be maximizing the share of some industrially relevant cells or, for example, killing all the cells which are in the states which are malign and harmful to us.
In particular, Kirill is looking at applying a technique known as control-based continuation, in which a stabilizing feedback controller steers the system through a sequence of steady states, which may potentially be unstable when trying to observe it open loop. Kirill made use of a proportional controller and also showed that this technique could be used to determine the equilibrium of individual genetic modules and then predict the equilibrium of the system when two of these modules are competing for resources.
Hello, I am Nick Marios Kokolakis, and I'm a postdoctoral researcher at the University of Pennsylvania. My research is about non-asymptotic safe reinforcement learning for trustworthy autonomy. First, I have addressed the problem of learning-enabled bounded rational multi-agent autonomy. The core idea is that, inspired by the theory of mind, we develop an interpretable level K thinking model to characterize the reasoning depth of bounded rational agents. Online learning enables autonomous agents to infer their opponent's thinking levels and adapt their strategies in real time. The second project that I have addressed is non-asymptotic reinforcement learning for safe autonomy. The core idea is that using Lyapunov design, we develop reinforcement learning algorithms with probable non-asymptotic convergence guarantees, enabling robust, safe, and time-critical decision-making in unknown adversarial environments. The third project is titled Physics-Informed Learning for Safe and Resilient Time-Critical Autonomous Systems. The core idea is that we develop an adversarial physics-informed self-supervised framework that synthesizes robust optimal control strategies with guaranteed safety and predefined time stability under worst-case disturbances. So, last but not least, the last project is titled Generative AI-Enabled Information Theoretic Control for Physical Autonomy. The core idea is that leveraging parallel computation, we develop generative AI-based information theoretic decision-making mechanisms to synthesize safe, efficient, robust, and adaptive predictive control strategies for autonomous systems operating in uncertain physical environments. By incorporating historical experience data, the framework iteratively improves system performance while robustly satisfying constraints across repeated tasks.
So, as you just heard, Nick Marios has worked on a ton of very cool areas, combining control with various aspects of machine learning. But I wanted to add a little bit more detail about his work on safe reinforcement learning. So, he released a paper earlier this year that looks at constructing feedback controllers to guarantee closed-loop predefined time stability. And this approach made use of a Lyapunov function that served as the solution to a Hamilton-Jacobi-Bellman equation. And the paper developed a critic-only reinforcement learning-based approach to learn this function in predefined time.
Hello, I am Parth Paritosh. I am currently a postdoctoral fellow at Army Research Lab. My work deals with networked estimation and inference, with the primary application area being networks of sensors. Typically, I want to design algorithms that are able to handle the time-varying nature of the estimates and make inferences in real time. Some of the questions that I am interested in, they stem from designing scalable algorithms, both in terms of communication and in terms of the variables that each agent tracks, and making these algorithms, adapting them for real-world sensors to be able to handle the data that we get from highly nonlinear settings. And more recently, I've been working on privacy and resilience in these sensing networks.
I was reading up on some of Parth's papers in this area, and this does seem like super interesting work. So in the first paper I was reading, the aim was to present a distributed estimation algorithm that could estimate a relevant subset of the total variables at each node. And because each node didn't have to estimate all of the variables, this reduced storage, communication, and computational requirements compared to more traditional consensus-based results. Another paper I looked at related to what Parth has just described, so it examined cooperative tracking of time-varying signals whilst preserving privacy, which in this context meant keeping the received signal private from eavesdroppers. I did this by extending the standard state decomposition approach and introducing a mixing step in the initialization to increase privacy whilst maintaining convergence of the estimation.
So I am Radosław Patelski. I am right now I'm postdoctorate researcher at INRIA in France. And at INRIA we are working mostly on finite time estimation, finite time control for systems. And while of course there are different methods to apply to come up with finite time algorithms, our goal is to apply those methods to epidemiological systems to study spread of epidemics in the population. And to do this, we had to adjust those existing methods to be able to apply them to this specific kind of systems. And we indeed achieved this goal. We were able to estimate number of infected people and number of exposed people using our methods. Right now, we may want to try this with real data, with real information, but the method works very well in simulation on theoretical level. So we hope that we can extend it also to more practical application.
In addition to estimation and control of epidemiological systems, Radoslav has also worked on designing observers for hovercraft, as well as a number of variations of active disturbance rejection control. So, active disturbance rejection control is a technique that can be applied to unknown systems by lumping the dynamics together into some disturbance term and then estimating this using an extended state observer. However, this still requires you to know both the order of the plant and its input gain parameter. So one of Radoslav's papers was carrying out online identification of this input gain in order to remove this requirement. Another of his papers was looking at how to combine this framework with a parameter identifying extended state observer, and showed that by doing this you could ensure asymptotic convergence of both tracking and estimation errors, as well as better transient performance.
Hi, my name is Carmen. I'm a postdoc at Stanford working with Professor Marco Pavone, and this year at CDC I organized a workshop on large language models and control, and I also gave a talk at the Control Architecture Theory workshop. In both my talks, I talked about how control theory can be used to control and also understand foundation models and generative models in artificial intelligence, and how we can study different levels of granularity within a foundation model with control theoretical tools. We can look at the attention mechanism with control theoretical tools and study the dynamics that lead to intelligence behavior. We can also zoom out a little bit and look at the layers that we have and understand how this depth can be seen as some propagating dynamics and how we can control the evolution of the inputs and outputs of these layers. And we can also zoom out a bit more and see the whole generative model and its whole behavior as some behavior that we can control, and we can study it with reachability tools, controllability tools, tools from optimal control. And I really think that studying control and AI offers a big opportunity for anybody in this community, and I encourage everyone to look at these topics.
I actually saw Carmen's talk at the Control Architecture Workshop, and it was so interesting. She was so enthusiastic about what she was talking about. It was absolutely wonderful to see. So, Carmen mentioned looking at AI architectures from different levels of granularity, so from the attention mechanism up to controlling the inputs and outputs of various layers. She's also written papers on how to embed generative AI models into physical systems, so for example, how to best interface these with more traditional controllers in the context of robotics. I also wanted to highlight a paper that she wrote on the use of state space models in deep learning architectures that was specifically aimed at control engineers. I really enjoyed reading it. I would definitely recommend it to anyone interested in that field. Quick summary of the work of all of these researchers. Amy Strong develops data-driven methods to compute invariant sets for constrained nonlinear systems. Anju Anand studies strategic communication using game theory, modelling how to transmit information under misaligned objectives. Brian Block designs computationally efficient controllers for traffic systems, models as partial differential equations. Declan Jag develops theoretical and computational tools that can be used to solve a wide variety of PDE-based problems. Hamza Al-Kabir advances fault-tolerant control with applications to robotic surgery. Kirill Seshkar uses control-based continuation to probe biological systems by steering them towards interesting equilibrium points. Nick Marios-Kokolakis develops non-asymptotic Lyapunov-based and physics-informed algorithms for robust autonomous systems. Parth Paritosh creates privacy-aware distributed estimation algorithms for time-varying networks. Radoslav Pastelsky uses finite time estimation to study the spread of epidemics. And finally, Carmen Alonso bridges control theory and AI by modelling deep learning architectures as dynamical systems. That's all from this mini bonus episode. I really hope you've enjoyed it. I, for one, really love meeting all of these researchers and hearing about their work and then reading up on their recent papers. So I do hope you found it interesting. I have left their details in the description if you fancy checking out their work. If you'd like to get in touch, you can connect with me directly or follow the podcast on LinkedIn. As I mentioned at the end of last episode, next month I'll be talking to a wonderful researcher that I interviewed at CDC about her work on game theory, and that'll be released on the 1st of February. But until then, have a fantastic next few weeks.